final piece that we're looking at in this chapter is the binomial distribution. It is a special case of our discrete probability distributions that we were looking at yesterday. So we know discrete, countable number of options. The binomial follows a very specific pattern. There has to be a fixed number of trials. They have to be independent, so one doesn't affect the other. There can only be two possible outcomes. Usually P is considered like success, Q, the opposite of that, 1 minus P is your failure. And the probability of success is the same for each trial. So for instance, if I say I'm going to flip a coin 4 times, and I want to know how many heads I get. That would be binomial. It's a set number of trials, so I'm doing it 4 times. Success is what in this case? Well, not the probability of it, just what I said I wanted heads. So a success would be getting a heads, failure would be tails. If I flip once, does it change probability that the next one would be a heads? Nope. And the probability of a heads is the same every time I flip a coin. That makes it binomial. So let's look at these and decide if they're binomial. A player rolls a pair of dice 10 times. The number of 7s rolled is recorded. So, do I have a fixed number of trials? Yes. A lot of times that's called n. The number of trials is n. Do I have 2 outcomes? Depends on how I'm looking at it. If I said I'm recording what number I roll, then that wouldn't be binomial. But here it is, because I want 7s. So the probability of getting a 7, that's my success. Failure would be not getting 7. Does that make sense? Alright, so my 2 outcomes. So this is binomial. Okay, an official with the FAA randomly selects airline flights until she finds 10 that were not on time. The number of flights that need to be selected is recorded. Okay, do I just have 2 outcomes? On time or not on time? Do I have a fixed number of trials? No. I am watching planes until I find 10 that were not on time. That means I might watch 10 planes. I might watch 50 planes. So it's not a fixed number of trials. That's not binomial.
Does it matter that the chance that they're not on time is not 50-50?
It doesn't have to be 50-50. It would just have to be the same for every plane. And we don't really have enough information to even decide that here. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number of females selected is recorded. So, do I have a set number of trials? Yep. Okay, do I have 2 outcomes? Female or not female? Okay. So does that mean it's binomial?
No.
Why?
Because each time you take a, say, female out, there's 1 less female, so that means it's a better chance that it's male the next time.
Right. You guys see that? Let's pretend, just keep it simple. We just did an art class. Okay, if I want the probability of getting a female, and first name I draw is Ava. She comes up here. What happens to the number of females sitting out in the crowd for me to select from? It goes down. So is the probability the same every time? No. So you could explain it that way. You could also say it's not independent. Picking Ava first changes the probability of a female getting selected the next time. So this one is not binomial. Because the trials aren't independent. Now, if I selected one person and then had them go sit back down and selected a new person, could that be? Yes, because I have the same group to select from every time. So what I want to do before I give you like all these formulas for how the binomial's done, I want to look at a scenario, kind of explain it. The 11 largest air carriers had an on-time percentage of 79% in May of 2008. Suppose that 4 flights are randomly selected from May 2008 and the number of on-time flights is reported. Construct a probability distribution for the random variable x using a tree diagram. We don't necessarily have to, but I want to make my probability distribution. That's listing every outcome and the probability of it. What are my possible x values? Oh, we were just looking at 11 air carriers, but we had. Is it possible that none of them were on time? So my possible x's are 0 through 4. Alright. So we have to somehow figure out what the probability is. I think one time I did show you a tree diagram, but you guys didn't overly like it. So do we just want to list out our combinations? So, is it possible that we said none of them are on time? So, can we just, you want to call it success and failure? So, if they're all late, that's 4 failures. Or, we could have 1 on time. Okay, so it could be the first one on time, and the other 3 late, or second one on time, the other 3 late, or the third one on time, the other one late, or the first 3 late and the last one on time. So you guys see I'm just trying to list all the combinations. Okay, 2 flights on time. So it could be the first and second on time, the first and third on time, first and last on time. That's every combination where the first one is one of them. It could be the second and third, or the second and the fourth, or it could have been the third and fourth. Right, or it could be 3 flights on time, so 1 late. So it could be the first one was late and the other 3 weren't, or the second one was late and the other 3 weren't, or the third one was late, or the last one was late.
Or they were all.
Or they were all on time. Okay. But computing a probability isn't even that simple. The probability of 0 flights on time. Okay, that means they were all late. They have a 79% chance of being on time. So the probability of being late is 0.21. And that had to happen 4 times, right? I took 0.21 times itself 4 times. So what would I get for that probability? 0.0041. I got 0.0011.
I squared it.
Oh, okay. Alright. So for 1 flight on time. So my 1 flight on time, that's 79% chance. 3 flights for late, that's 21 3 times. How many times in my scenario did I get 1 flight on time? Four of them? So I'd have to take this times 4 if I'm adding all those together. Okay, or if 2 flights are on time. So that means my 0.79 was twice and my 0.21 was twice. How many combinations had 2 flights on time? 6 times 6. So that probability is 0.1651. Right, 3 flights on time. So my chance of on time was 3 of them. My 21 only happened once. How many combinations had 3 flights on time? 4. I get 0.4142. And my last one, 4 flights on time. So the probability of being on time, 0.79, that happened 4 times. How many combinations had all 4 flights on time? Just one of them. That's 0.389. Alright. So that was a little time consuming. And we only had 4 flights. You can imagine if I wanted to look at 10 flights, how long this process is. But it's really the same thing every time. Okay, if I looked at this first one, there were no flights on time, so nothing had a probability of 79. All 4 had 21. Here, 3 of them had the 21, 1 had the 79. 2 had the 21, 2 had the 79. Okay, so we see this pattern. Here, this one, there was nobody that was late. These numbers in front, that comes from counting our combinations. So there is a formula for how this is done. This is the binomial distribution, a shortcut for that. So it's n choose x, p to the x, 1 minus p to the n minus x power. That looks a little confusing, but think about that scenario we just did. In it, my n was 4, because there were 4 flights on time. The probability of being on time is 0.79. If you look on your calculator, so if I wanted to do this calculation for my probability, and there are 4 flights, I need to choose 0. This is a counting principle, it's a formula. I'm not really going to go into it. You covered it at the very end of Algebra 2, I think, if you had time, but for now you just need to know how to do it. So if you hit the Math button, well, first type the 4, and then if you go Math, and over to probability, the third one down says NCR. So if I said 4 choose 0, it gives me 1. Where did we see 1? Over here. Is that just like my coefficient right here? If I did 4 choose 1, there are 4 flights and I want 1 on time. It tells me there are 4 of those combinations. If I did 4 choose 2, so 4 flights choose 2 to be on time, it gives me 6. If I do 4 choose 3, it gives me the 4. So that formula gives these numbers in front. Does everyone see where I'm getting that? Okay, is everyone getting that? So that gives us the coefficient. And then it says p to the x. So we had our 0.79 to the 0, 0.79 to the first, the second, the third, the fourth. 1 minus p to the n minus x. If I have none on time, 4 of them are late. If 1 is on time, 3 are late. 2 on time, 2 early. Okay, and that's where that formula comes from. So it is a much faster way of doing these calculations versus us counting out how many times it can happen and calculating all of those probabilities. All right. So let's try this. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? So first, what is my N? How many households are we looking at? 1. So I have a fixed number of trials. P, what's the probability of 3 or more cars? 0.35. Okay, and that's the same for everybody. Only 2 outcomes. They have 3 or more cars or they don't. So the probability that 5 have it, so that would be N, choose 5. You can type that in parentheses when you put it in. P, 0.35 to the X, so if 5 are on time. 1 minus P. What's 1 minus 0.35? 0.65. If 5 have them, how many don't? 15. Okay, I want you to type this in on your calculator. Use your parentheses. Probability 0.1272. Did you get it?
Yeah.
Awesome. Okay. B. What is the probability that less than 4 have 3 or more cars? Okay, that's kind of annoying, but we can do it. Less than 4 means it could be 0, 1, 2, or 3. Okay, don't make life hard. You already have this typed in your calculator, right? So bring it back up. To find the probability of 0, you would do 20 choose 0. 0.35, we want that to happen 0 times. 0.65 then would happen how many times? 20. Right? What do you get for that decimal when you type it in? 1.812, and the end it has e to the negative 4.
So move the decimal to the left.
0, 0, 0, 1.
Yeah, I'll go ahead and put 0, 0, 0, 1. Okay, so that's for 0 cars. Okay.
What exponents did you change? You changed the 5 to
So I did 20 choose 0. So 0.35 happened 0 times, and 0.65 happened all 20 times. Okay, then we have to do 1. So you can bring that back up. 20 choose 1. 0.35 to the first, and it would be 0.65 to the 19th, right, because they're 20 altogether. And that gives us?
0, 0, 2.
Yeah, or, yep. Unless you want to keep 195, you could do that too. But. Okay, so for 2, it would be 20 choose 2, 0.35 to the second, 0.65 to the 18th, and we get 0.00998, so 0.01. And we also need 3. So 20 choose 3. 0.35 to the third. 0.65 to the 17th. Do we have some rounding error here?
What?
Absolutely.
Oh,
Oh, you just did one more. We stopped at 3. Okay. I want you to get out your formula sheet. Okay, if you flip to the back of this, the back 4 sheets of paper, table 3, it says binomial distribution across the top. This is a table of some options. Now, is everything going to be on here? Absolutely not, but some of them are. So in this case, my n was 20. So if you look, the n values, it has all of them at first, but after you get to 12, it just jumps. If you look at the very back page of your formula sheet, you see a chunk where n is 15, and the bottom half of that table is when n is 1. Okay, does everybody see that? What was my probability on this one? 0.35. So if I go over to the 0.35 column, so 20 choose 0. So you see the 20 first, the next column beside that is your x. So when your x is 0, if you go over to 0.35, what was our probability on this table? 0.0002 is what I see. Right here. Yeah, we're looking when n is 20.
Oh,
You were looking at 50. So when n is 20 and our x is 0. And we had 0.0011 or 0.00018. Does that round to the same?
I mean, where are you?
Right here, because I was just looking at when I wanted 0 of them to have the same number.
yeah.
So if I wanted 20, remember we did 3 or less than 4, so when x is 1. So if I go to my 20 when x is 1, over to my 0.35, it had 0.0020. Okay, when x was 3, right below that, 0.0100. When x is 4, right below that, 3, 0.0323. So it has some of them here. Now I showed you how to do them by hand because not every probability is across the top. You know, if I said 31%, that's not there. They go up by increments of 5.
So,
And it doesn't have every
what's
possible
on that sheet is what we just did there.
Yep. So this is a table with some of the common ones already calculated for us. So using our table, let's answer the next question. Or I guess this one we don't really need to. What's the probability that at least 4 have 3 or more cars? How do we do at least 4?
Be
Add
1.
4. With the 4.
Well, it means 4 or more. So we could add up 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Or
We could just do 1 minus 0.0445.
more than, we did less than 4 up here. This is 4 or more. They're complements. So we could just do 1 minus what we already did. Or calculate it from the table. Either way,
How would you calculate?
you would add up all of them. So we get 0.9555. What's the probability that between 3 and 5, let's say inclusive. Usually I'll say that. That means including 3 and 5. Have 3 or more cars. So that means it could be 3, 4, or 5. Let's do that from our table. So when my n is 20, my p is 0.35, I want to add up when x is 3, 4, and 5. you guys see how I got the numbers I added together? Does everyone understand how to read this table? Okay. One thing I want to caution you on there is a lot of potential for rounding error. It's not going to ever make a significant difference, but this table, everything's been rounded to 4 decimal places. If I calculated each of these probabilities and kept them to 6 decimal places before I added them, could my answer be slightly different? Yes, but it'll just be that last decimal place that varies. So just note that these are rounded values in the table. All right.
And also be careful to not get on the wrong one.
Yes, it is. There's a lot of numbers. So it can help to have like some sticky notes to make sure you're in the right column, kind of covering up things. That's very helpful. You'll also notice there are several, like when n is 15, that first column, the 0.01s, you'll notice going down there's a lot that say 0, 0, 0, 0 plus. That means it's a positive number, but all the first 4 digits are 0. So the probability isn't truly 0, it's just so small, all of those digits are. Okay. Questions there?
So all of these are if the number of things like the cars is 7 or 6 all the way to 20.
You're lost. Like you can't read the table, or where?
It's just,
Yeah.
I think I got it.
So you're not really lost. You just don't like it.
It's just a little bit, it's just a lot.
It is a lot. We're not done yet.
It's hard to remember.
What?
Like-
There's more.
There's more notes. Like
I'm
there a lot of
Today?
yeah, like today. We're doing more. Okay.
So, just like anything else, we need to be able to find a mean and a standard deviation, just like we're doing for other probability distributions. The setup is easier on these. The formulas are very straightforward. So the mean is just n times p. The number of trials times the probability of success. Standard deviation is the square root of n times p times 1 minus p. Just like all the others, it's on your formula sheet. Okay, nothing special we have to do there. So let's look at this example. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and standard deviation of the car-owning households that have 3 or more cars. So how do I find my mean? My number is 400, probability is 0.35, so 400 times 0.35. Standard deviation is the square root of n times p times 1 minus p. So the square root of 400 times 0.35, what's 1 minus 0.35? My standard deviation is 9.5394.
Why is it O or sigma or whatever that is instead of S?
It technically could be either one. For a distribution, we're assuming like a population, it's a sample. But it's just the notation they use. They don't distinguish between population and sample on the whole distribution. All right. Last one of the day. 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, find these probabilities. So what is my N in this case? What is my P? So, part A, exactly 10. So that's like saying X is 10. I want everybody to go to your binomial table. You need to find when N is 15, P is 0.65, and when X is 10, what do we get? Did you find that number, Grady? Does anyone need help finding that number on the table? Speak now, or you can't complain on your homework that you don't know how to read the table.
Table makes sense.
So N is the total number of people,
It's the number of trials.
X is the number of,
Yeah, N is the number of trials we had, so we only talked to 15 people. X is out of those, how many said yes? 10 of them. So B,
so if you're finding the percentage that of people that said yes, you divide 10 by 15.
no more than 6. So if it's no more than 6, what could X be?
0.
1, 2, 3, 4, 5, 6.
Okay, so we could do those. Could we also do 1 minus 7, 8, 9, and 10? Yeah, doesn't really matter, we're just reading from our table. So go to your 0.65. If you need a sticky note or another piece of paper to cover it up, you can. If I'm adding up those probabilities, the first couple are zeros. When it's 2, 3, 4, 5, and 6.
So if it's like the 0 plus, we like don't even count it.
Yeah, just leave it off. All right. Questions here? So this is where I'm stopping today. Tomorrow, we're going to practice this some more. Okay? There is a handout posted on Classroom, but it is not due until Monday. Because we're going to practice more and make sure everybody feels good about it. So you're welcome to start it, but you don't have pressure to finish it for homework. Okay, tomorrow we'll do some practice. I'll give you some time in class to work on your own and check. And then the handout will be turned in